The last video for section 2.3 is about the order limit theorem, which we abbreviate OLT. And this is just a theorem about how if you know that the values in a sequence or in two sequences behave according to a certain order, meaning they satisfy an inequality, and you know that those sequences also converge, then you should expect that the value of the limit of those sequences would also have to satisfy that same ordering that's imposed from the inequality on the terms. So I'm going to demonstrate how to prove part 1 of the OLT, and I argue that parts 2 and 3 can be thought of as corollaries of part 1, where if we can show 1 is true, then we can just reconceptualize 2 and 3 to actually make them look like an application of 1. So here we have a sequence. We say that an is greater than or equal to 0 for all n. So all of my terms in my sequence are non-negative. We need to argue that because we also know that an converges to a, this means that its limit a has to be non-negative. It can't suddenly jump and be negative. So I'm going to use a topological picture to describe this, although I'll show you how you can also do our usual XY depiction. But one of the things that we should answer is why can't a be less than 0 when an is greater than or equal to 0 for all n, and an converges to a. So to prove that a is greater than or equal to 0, we're going to think about why it can't be negative. So here's 0, and we know that our sequence lives entirely over here. It can't be negative, the terms. So let's suppose that a was negative, and we'll put it right here. What I would do is pause your video and ask yourself, what would be wrong with this picture? What about our assumptions is violated? And how could you show this precisely? So the issue here is that we know that when you converge, your points from your sequence that are converging are supposed to approach A, and they should be able to get as close to A as we specify. But notice that for us, our terms cannot go past 0. And so somehow these terms are supposed to converge to A by jumping over and somehow skipping all of this space right here. So there can't be any terms in this neighborhood that I've drawn. So whatever this neighborhood is, my V epsilon of A, it contains no negative values. So on the one hand, all of my whole entire tail is supposed to be in that neighborhood, but on the other hand, I know that none of my terms in the sequence can be inside that neighborhood. Now there is something important here about the neighborhood that we've selected, because I couldn't use this argument on just any epsilon neighborhood. We have to choose an epsilon neighborhood that only contains negative values, which means the radius of our neighborhood can't extend past 0, because then I wouldn't be able to say for certain that there are no values of the sequence inside my neighborhood. So the key here is we want to choose epsilon to be less than or equal to the absolute value of A, so that V epsilon of A contains only negative numbers. So, but then, no ANs are in V epsilon of A. However, AN converging to A implies the entire tail is in that neighborhood. And that's a contradiction. So I'm going to write up this proof formally. Before I do that, I'll draw you a quick sketch of how I could depict this in our typical way that we make sequence pictures on an XY plane. So I would have my A down here. And the neighborhood that I'd be making my V epsilon of A would be between this range, like that. And that's my epsilon band. So on the one hand, all of my values in my sequence have to be up here, and they're supposed to converge down to A, but they're not allowed to go past 0. So they can't ever enter the epsilon band. Okay, so let's write up the proof. Oops. Proof. So we get to assume that AN converges to A, and that AN is greater than or equal to 0 for all N. Suppose toward a contradiction that A is less than 0. So remember how our argument went when we were drawing our picture. We put A less than 0, and then we said, oh, we need to get the epsilon neighborhood whose radius is such that the neighborhood only contains negative values. So we're going to choose a value of epsilon. So we're going to let epsilon equal, it doesn't matter what value we pick, as long as epsilon is no greater than the absolute value of A. So let epsilon equal the absolute value of A, or any other value such that 0 is less than epsilon, which is less than or equal to the absolute value of A. Now technically you wouldn't need to say that in a proof. I'm just including that here for conceptual understanding. So by construction, V epsilon of A contains only negative real numbers. Thus, AN is not in V epsilon of A for all N. Because remember, all of my ANs were non-negative. However, since AN converges to A, for this epsilon, there exists a capital N in the natural numbers, such that for all N greater than or equal to capital N, little an is supposed to be in the epsilon neighborhood. That is our contradiction. I mean, in particular, for example, a sub capital N is supposed to be in our neighborhood, but we just said no values are in there. Thus, A must be greater than or equal to 0. And we're done. So earlier I said that the other parts of the order limit theorem can be restated so that they're just applications of part 1 that we've already proven. So I would like you to pause the video and think about how can the statement that's in the second part of the OLT be rewritten so that it looks like part 1. So here, just a reminder, in this case we know AN converges to A and BN converges to B. We want to argue that if AN, the terms of AN are always less than or equal to the terms of BN, then that means that their limits have to be ordered in that same way. A has to be less than or equal to B. So how can we rethink this as a statement about a sequence having its terms greater than or equal to 0, necessarily implying that its limit has to be greater than or equal to 0? So the key here is to rearrange the inequality AN less than or equal to BN. We want to make it instead BN minus AN is greater than or equal to 0. Then this sequence that we have right here is kind of playing the role of AN in part 1. So we can call this our CN. Can we just use part 1 at this point? What are the assumptions that are necessary? So let's go back up and look at part 1. Part 1 says that if you know your sequence converges and all the values are greater than or equal to 0, then the limit has to be greater than or equal to 0. So here I have Cn, all of its values are greater than or equal to 0 for all n. Can we just apply the OLT? Not yet. We have to make sure that Cn converges. So in order to use the OLT, you need to know that the sequence whose terms are ordered a certain way is also a convergent sequence. So we need to know, does Cn converge? Well, Cn is Bn minus An. This is an application of the ALT. Yes. Since An converges to A and Bn converges to B, by the ALT, the algebraic limit theorem, An minus Bn has to converge, Bn minus An, doesn't matter, but Bn minus An has to converge to B minus A. So, sweet. That means we have a sequence that all of its terms are greater than or equal to 0, and it converges. So really what we're saying here is that Cn converges to B minus A. So by OLT part 1, its limit, B minus A, has to be greater than or equal to 0. Rearranging, that's just A is less than or equal to B. Now you can do something similar for part 3. Part 3, it's just that C is C is a constant here, and C is playing the role of one of the sequences. So you could think of, like, I could apply part 2, I could say I'm dealing with when I'm looking at C less than or equal to Bn, I could think of C as terms of a constant sequence. namely the sequence C, 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 and then I can just apply part 2. And then in the second inequality, I can think of here as, again, C is going to be the terms of a sequence Bn, for example, and it's all constant. So as always, though, I want to make sure that we're careful with our assumptions here of the OLT. And so your warning: cannot use the OLT unless we know AN and BN converge. Well, if we're using part 1, we just need to know that AN converges. And that's it.